In our last module, we gave a brief introduction to the wiring diagram and talked about computers. Having a basic understanding of the inner workings and terminology of computers is going to help us out in the next few modules. Today, I want to continue on the last module and talk more about communication between computers. In particular, I want to discuss the concepts of analog and digital communication and how they apply to what we do. Let's look at GPS as an example. GPS receivers capture the transmissions from the GPS satellites using an antenna, which is attached to the receiver by a coaxial cable. As we talked about in the GPS modules, two different frequencies are used, L1 and L2. These are analog signals, or signals that are continuous and smooth as time progresses. They're also called carrier signals, because they don't actually contain all of the position and timing information we need. They just carry another signal that does. The carried signals for L1 are the course acquisition or CA code and the navigation message, which are digital signals or signals that are only composed of two states. The process of mixing two signals together is called modulation. GPS uses a specific kind of modulation known as binary phase shift keying or BPSK, which gives us a great segue into binary. Most normal non-engineer types count in decimal, or a base 10 system where you have 10 different values from 0 to 9 to use. Binary is a base 2 system, in that you only count in zeros and ones. Binary comes from the computer's need to store numbers on transistors or vacuum tubes that can only be held in an on or off state. If I was to count to 4, I would only need one decimal digit, but in binary, I'd need 3 digits. Each of these digits is called a bit, or binary digit. 4 bits is a nibble, and 8 bits is a byte. The 60s were a pretty weird time. Anyway, why do we need analog and digital signals in the first place? Well, the short answer is you can't transmit just a digital signal over the air. Digital signals don't really exist in nature. Things like sound waves and radio waves are analog by nature, as they change continuously over time. So when the GPS satellite uses its radio transmitter to send a signal down to us, that is an analog signal carrying the digital information. The problem is that in order to do the processing to get a good position, we need to isolate the digital from the analog. See, computers are by nature digital devices and can't really understand analog signals. This can be done several different ways. We're going to simplify things and just talk about using an analog to digital converter, or ADC. The basic principle here is that you're taking your continuous analog signal and sampling or measuring it to build a digital signal on the other end. You're then taking those measurements and quantizing them, or representing their values as integers in binary. Receivers also do things like amplify the weak signal you get from the satellite and filter out noise from outside sources. The receiver is also going to take that input signal and build a standard message that your sonars and computers and all of your other equipment are going to receive over the serial cable and use to derive GPS position and timing. Okay, so that might have seemed like a long way to go for something that isn't really shown on the wiring diagram. But this leads us into a discussion of something that is important to understand: dynamic range. Check out our ADC. How many measurements are enough measurements? Well, the more measurements you make, the more numbers you're going to have to store and move around. If you're just trying to get that CA code from the carrier frequency, you need enough measurements to capture those phase changes. But what about the kinds of pressure waves our sonars measure? Well, let's take the Klein 5000. It has a 12-bit analog to digital converter. That means that when you get an analog return, aka a sound wave from the seafloor, and you're looking at intensity versus time, you can digitize that signal into 2 to the 12th or 4096 levels. The more levels you have, the better the representation of the actual intensity of the original signal. The better the signal, the better the backscatter image. Check out this image. Here, you can see that the 8-bit dynamic range seems to be enough to cover the signal. But 8-bit range gives you only so much detail in your mosaic. Of course, this isn't a magic tool to get you better backscatter. At some point, the return you get from increasing your dynamic range is going to diminish as you catch up to the detail present in the original analog signal. There are several ways to calculate the potential dynamic range of a signal, which I'm not going to go into here. You can also calculate the rate at which you should sample a signal, which is known as the Nyquist rate and is equal to twice the frequency of the original signal. You might have heard of anti-aliasing in the audio world. Fun fact, aliasing is just the bad conversion of analog to digital because of a bad sampling rate. Anti-aliasing is a technique for fixing that problem after the fact. Okay, I think that's enough for today. Let's do a quick wrap-up. We talked a little bit about how analog and digital signals differ, and how they come up with regards to GPS and sonar technology. We've also talked about how to convert between the two, and about binary, which is the counting system in the digital world. And finally, we talked about how you do that conversion well, with sampling rates and dynamic range. If you see dynamic range come up in some sales literature in the future, now you know what it means. So where do we go from here? Well, this all gets us to the point where we can finally start talking about cables and communications. You'll need to keep some binary and ADC stuff in your head for this, so don't think we just went off on some tangent today. Thanks for watching, and good luck out there.